iPad connect பண்ணிட்டீங்க. Okay. Shall we get started? Right. So till previous class, we discussed the basics of magnetism, right? So what
Sir,
was the last topic?
I can't see the screen.
Sorry?
I can't see the screen. It's in the presenter mode.
Is it okay now?
Yes, sir.
So yeah, tell me. So what were the concepts we saw in the previous class? So basic properties of magnetism. Now what we'll do is we'll see some important definitions that are connected with magnetism. Okay. So we'll see some important definitions that are connected with magnetism. The first one is, let's see what is magnetic field. So this is known to us, right? It is a space around a magnet within which its influence can be experienced, right? So if you take a magnet, right? If you take a magnet, what is going to happen? This magnet is going to have a region around this where you try to bring in another magnet, it will start experiencing force, right? See, for example, this region where, see, I'm trying to hold it, it's getting attracted, right? So there is a region around this which is called as the magnetic field. Secondly, when you talk about this magnetic field, you can have two types of magnetic fields. What are they? One is going to be uniform and the second is going to be non-uniform. So what do you mean by uniform magnetic field? It is a magnetic field in a region. So a magnetic field in a region is said to be uniform if it is going to have the same magnitude and direction at all points. So at every point, if the magnetic field is going to have the same magnitude and direction, so it is going to be a set of parallel rays, right? This is what is called as uniform magnetic field, and we have discussed about this a lot in the previous chapter itself, right? So what will happen at a given place, the magnetic field of Earth can be considered to be uniform, but when you think of a bar magnet, right? When you think of a bar magnet, its magnetic field is not uniform. Okay. Third important point is magnetic poles. So what are the magnetic poles that we know? A magnet has a north and a south pole, right? So these are the regions apparently concentrated, which have the concentrated magnetic strength in a magnet. So these are the regions of apparently concentrated magnetic strength in a magnet where the magnetic attraction is going to be maximum. So it is the place in a magnet where the magnetic attraction is going to be maximum. And the most important point is the poles of a magnet are not going to lie exactly at the geometrical ends. This is not considered to be a pole, or this is not considered to be a pole. The pole is always going to be slightly inside the geometrical ends. Am I clear with that? So the poles of a magnet lie somewhat inside the magnet, and they are not going to be exactly at the geometrical ends, right? So having said that, when you have defined the magnetic poles, the next two important points that we need to define are magnetic axis and magnetic equator. Okay. So what do you mean by magnetic axis? So what do you mean by magnetic axis? So if you think of an imaginary line, right? If you think of an imaginary line that is passing through the poles of the magnet, that is the north pole and the south pole. When it is passing through the poles of the magnet, you call that to be magnetic axis. So what is the magnetic axis? The line passing through the poles of a magnet is called as the magnetic axis of the magnet, right? Then what is this magnetic equator? So magnetic equator is going to be a line, right? It is going to be a line that is still going to pass through the center of the magnet, but, right? It is going to pass through the center of the magnet, and it will be at right angles with respect to the magnetic axis. Meaning, if this is the magnetic axis, if you think of a line which is perpendicular to it, at the same time passing through the center of it, you call this line as magnetic equator, right? That's what this point is. And the last point that we need to understand is what is magnetic length. So we understood from the third point that the magnetic poles are not going to lie exactly at the geometrical ends. They are going to lie slightly inside. So if you are able to measure the distance between the magnetic north and the magnetic south, which is present inside the magnet, then that is what is called as the magnetic length. So when you talk about length, right, there are two types of length. One is going to be magnetic and the second is going to be geometrical. So geometrical is measured from one end to another, whereas magnetic is measured from one pole to another. If you observe the diagram itself, one thing would be clear that the magnetic length is going to be always less than the geometrical length. That's obvious from this statement itself, right? So this is all about some important definitions which are needed to understand magnetism. Okay, make a quick note of it. Done. Done. So the next point that will, you're copying, huh? So we'll see the next topic, that is Coulomb's law of magnetic force. Okay. See, before we see the concept of what is Coulomb's law, first thing that we need to understand is a term called as pole strength. Okay. So name itself is suggesting something. We know what is a pole, we know what is strength, right? Try to combine, it will give you some idea of what it is, right? So the pole strength of a magnet has some significance. What do you think it is going to show? It is going to speak about the extent of strength a particular pole is going to have, right? So the pole strength of a magnet represents the inherent strength, in the sense its natural strength of its magnetic poles in exerting a magnetic force. See, I'll just give you a simple example. Let's say there is a magnet of this size and there is a magnet of this size, okay, a bigger size, right? Let's say the same amount of material, everything is same. Only thing is this is just an extended version. Out of those two, they have, how many poles are there in total? Here 2 poles, there 2 poles. Let's take 1 pole in each into consideration. North pole from this, north pole from the bigger magnet. Which one do you think will have a greater pole strength? Why do you say that? Because size is there and that pole will have more tendency to exert force on the magnetic substances. See, listen to this, okay? In this chapter, one point that you need to have in your mind is understand what is a magnet and what is a magnetic substance. Okay, so listen, if I take a nail and I'm going to connect it to this, okay, there is rust and all those things, but yeah, if I just connect it like this, it's getting stuck, no? So the substance which is experiencing the magnetic force is what is called as the magnetic substance. So going forward, if I use the word magnetic substance, you need to think of the substance which will experience force, and magnets exert force. So when you talk about the pole strength, you're obviously talking about the magnet, because that is the one which can exert force. Now connect all the dots and try to understand what the definition has to tell us. So the pole strength of a magnet represents the inherent strength of a magnet, right? Inherent strength of one of its magnetic poles in exerting magnetic force. So it will exert magnetic force on a magnetic substance. So that is the test with which we can find out how strong the pole is going to be. Are you able to understand? Right? So in your lower grades, I'm not sure if you have done this, you can take some iron filings particles. You know what are iron filings, right? Right? Those particles and just sprinkle around the magnet. what will happen? Something like this will happen. No? Something like this is going to happen. Means if you are able to see more amount of the iron filings around a particular pole, then what can you conclude? More is going to be the pole strength because it is able to attract more magnetic substances towards it. That is one of the tests that you can do. So when I say test, no, see, for example, when we discuss the concept of electric field strength, you remember, if there is an isolated positive charge or an isolated negative charge, how will you test the strength of that? By bringing in a test charge close to it. The extent to which the test charge is able to experience force decides the strength of that particular charge. In a similar way, here also, you can do this kind of a testing, right? So having said this, right, the first thing that we need to understand is pole strength. I think we have seen the definition. So it basically speaks about the strength of a particular pole in a magnet, okay? Next is, it is measured value, right? It quantifies the pole's ability to attract or repel other magnetic materials. Are you able to understand? Magnetic materials and magnetic substances are the same. In the example which I gave you, what is it? It's an iron nail or iron filings, okay? So I hope this part is clear, no? With this, we will start understanding what does Coulomb's law state. Okay, we'll see the statement of it. So this law states that the force of attraction or repulsion, right? Between what? Between two magnetic poles. So I have a north pole and I have a north pole. If I'm interested to calculate what is the force of attraction or repulsion that is going to exist between them, right? It is observed to be directly proportional to what? It is observed to be directly proportional to the product of their pole strengths. So pole strength is represented by the symbol Q and the subscript M. If you just write it as Q, it is meant as electric charge. If you write M, it is understood as pole strength. It is not magnetic charge. There is nothing like that. It is a pole strength. Okay. So Fm is directly proportional to the product of the pole strengths, right? And obviously, it is going to be a similar pattern. It is going to be inversely proportional to the square of the distance of separation between them. Now, when you're going to combine both, Fm is directly proportional to Q1 into Q2, the whole divided by R square. So Fm will be equal to how much? 1, correction. So Fm will be equal to mu naught divided by 4 pi into, Qm and Qm. It is directly proportional to mu naught divided by 4 pi into Qm divided by R squared. So if you observe, is it not similar to the Coulomb's law that we dealt in electrostatics? So going forward, what you need to remember is, wherever you have this 1 by 4 pi epsilon naught, you need to replace that in magnetism with mu naught by 4 pi. Everything else is almost the same. Are you able to understand? So this is what the mathematical representation of Coulomb's law is. Am I clear with that? So make a note of it. You're done, right? In. ஆரம்பிக்கிறேன். Wait பண்ண மாட்டேன் சீக்கிரம் பண்ணு. Done. Those who have not completed, leave some space and copy it from others. We'll go to the next topic. So the next topic is going to be magnetic dipole and magnetic dipole moment. So this is a concept that we have discussed in the previous chapter itself, if you remember. So what is magnetic dipole? Name is suggesting. Magnetic dipole means it consists of two magnetic poles, right? Then what is the magnetic dipole moment? In the previous chapter, if you remember, we discussed magnetic dipole moment as N into I into A, where N is going to be the number of turns, I is going to be the current, and A is going to be the area, right, of the coil. But here, this is related to current carrying conductors. In the sense, this is related to electromagnets. But here, all that we are discussing is about permanent magnet. So when you talk about a permanent magnet, the same magnetic dipole moment is supposed to be expressed in terms of pole strength. It is to be expressed in terms of pole strength, and area will be replaced with length. Okay. So just to recollect the concept of dipole moment from electrostatics, can you tell me what does the electric dipole moment mean? So P is equal to magnitude of either of the charges into the distance of separation between them. That is Q into 2A, right? Now observe what is going to happen here. First, we'll understand what a magnetic dipole is. Magnetic dipole is basically an arrangement of two equal and opposite magnetic poles. What do you mean by equal? They are equal in terms of magnitude and opposite in terms of nature, right? So equal and opposite magnetic poles separated by a small distance is what is said to be a magnetic dipole. Okay, at least for the theory purpose, we'll consider only the small magnets. Okay. Secondly, what is a magnetic dipole moment? Now look at this. What do you think is going to be replaced in magnetism in place of charge? So it will be the pole strength, no? So magnetic dipole moment of a magnetic dipole is defined as the product of its pole strength and the magnetic length. So magnetic length is taken as 2L. Why do we take it? Again, the same logic. Why did we take it as 2A there? Because all the distances are measured from the center. So that when you break it into two sides, it will be A and A. Same logic, 2L. Okay. So what is it? It is defined as the product of its pole strength and the magnetic length. So it is going to be Qm into 2L. So magnetic dipole moment is going to be equal to Qm into 2L, where Qm is called as the pole strength and 2L is called as the magnetic length of the dipole. And magnetic dipole moment is measured from which direction to which direction. If you take an electric dipole, then how is the dipole moment measured from? It is measured from the negative to the positive charge. So negative charge here is similar to south pole and positive charge is north pole. That is why magnetic dipole moment is in the direction of south to north. So are you able to connect the dots, right? And the next important point is what is going to be the SI unit of it? It is obvious. So here, what was the SI unit? N does not have unit. I is measured in ampere. A is measured in meter square. Ampere, meter square. It's going to be the same thing. So the strength of the SI unit of magnetic dipole moment is going to be ampere meter square, right? Sorry. Ampere meter is for pole strength. So ampere meter square is the magnetic dipole moments SI unit. The other unit that we can use is joule per Tesla also. We can use joule per Tesla. Is that clear? So this is all about magnetic dipole and its dipole moment. Just make a note. ஈஸ்வர் அதுல அந்த வீடியோஸ்ல எதெல்லாம் blur இருக்கு சாரி done. Shall I proceed? So the next concept that we'll see is what are magnetic field lines. There's something similar to the electric field lines or electric lines of force, right? See, if you're asked to draw the electric field lines, what will you do? If you need to draw the electric field lines for an isolated positive charge, what will you do? So it is outward, okay, but how will you draw that? Like, how did you know it is outward? See, this is Q. You use something else, no, to test it. What is it? You use a test charge, no? You use Q naught here, right? So Q naught by default is going to be positive. It's positive, right? So Q naught by default is going to be positive. And due to this positive charge, it will experience a force away. Make sense? So what did I say? Q naught, this is the isolated source charge that we have considered. Q naught is a test charge that we have placed. By default, it is positive. So this charge due to the source charge will experience a force outward. So it clearly says that the electric field line's direction is decided by the direction in which the test charge experiences force due to the source charge. Bringing the similar context here, if I give you a magnet, we cannot think of an isolated north or a south pole. It is always as a dipole. So when I think of a magnet, now what is the test piece that I can use to find the direction? So here I have Q naught, but what can I use here? You can use another magnet, or you can think of a other magnet. You can think of a compass also, because compass also has a magnetic needle. Now the question is, here we are saying that the direction in which the positive test charge is experiencing force will decide the direction of electric field. Here, what is similar to positive charge? North pole, meaning when you place a compass here, the direction in which the north pole of the compass is going to point will give you the direction of magnetic field at that point. So what you're supposed to do is, if you take this magnet, right, you're going to take a small compass and place it here. The compass will show a response in such a way. Obviously, here there is north pole. According to the basic properties of magnet, the north pole should be away from it. So south pole will come close, north pole will be in this direction. So what you need to do is mark this point. After that, what you will do is take this compass, place it here. When you place it here, you can see a slight angle shift that will take place inside the compass. After that, wherever the north pole is going to stop, at the end, at the tip of the pointer, put another dot. Right. Again, take this compass, keep it here, repeat the process. Right. Repeat the process till you reach the other end. When you reach the other end, you will observe that the north pole has completely got aligned towards the south pole. That is obvious, because unlike poles are going to attract. So after that, what you need to do is, these dots you have placed, no, actually multiple compasses are drawn. It is only one compass. So with that, you have formed all these dots. What you need to do is join all these dots. When you join them, what are you going to get? You will get an imaginary curve like this. And this is what is called as the magnetic field line. Okay. So we'll go back to this concept. Let's say there is an electric field line like this, right, which is in this direction. If I'm interested to calculate the direction of electric field at a particular point on this curve, what will I do? You will draw a tangent, no? So you place it here, you're going to draw a tangent. If it is here, you're going to draw a tangent. What is the meaning of this tangent? The meaning of it is, if you place a test charge Q naught here, that Q naught will experience a force in that particular direction at that place. In a similar way, here what will happen? The same logic is to be followed. After you have completed the magnetic field line, at that point, if you are able to draw a tangent, then that gives you the direction of magnetic field at that point. Is that point clear? Is that clear? So it is clear that for magnetic field lines, unlike electric field lines, where electric field lines do not form a closed loop, magnetic field lines form a closed loop, so that outside the magnet, right, outside the magnetic field is from the north to the south pole, and inside it is going to be from south to north. Inside it is going to be from south to north. Clear with this? Let's make a note of it. School. Any updates? School. Short time. Slot time. 1.5 hours or 1 hour? 1.5 hours. எல்லா ஸ்கூல்ஸும் பண்ணுவாங்க 1.5 hour slot. பட் என்ன எல்லா சப்ஜெக்ட்க்கும் அப்படிதான் இருக்கா? போர்டு இல்லைல்ல 11th போர்டு எக்ஸாம் பண்ணாங்கன்னா நல்லா இருக்கும். ஈஸியா சொசைட்டி ப்ரெஷர், பியர் ப்ரெஷர், அது வேற எதுவும் இல்லை. Palama, shall we go to the next topic? Okay. So the next one is going to be a derivation. Next one is magnetic field of a bar magnet at an axial point. Right. So we need to derive this expression with the help of Coulomb's law. Now what I'm going to do is I'm just going to take some connections from the electrostatics and then put it here. We know that the definition of electric field is given as the amount of electrostatic force experienced by the unit positive test charge. So Fe divided by Q naught. This is the electric field strength. In a similar way, if I'm interested to calculate what is the magnetic field strength, what do you think will happen? The electrostatic force should be replaced with magnetic force divided by the test charge. You replace it with the pole strength of a north pole. Makes sense? Right. So suppose I have two poles whose pole strengths are Qn or Qm and Qn. Qm and Qn. Right. What is going to be the force between them if the distance of separation is r? So F will be equal to mu naught divided by 4 pi into Qm into Qn, the whole divided by r square. If I take this and substitute it here, what do you think is going to be the value of B? So if I take this and substitute it here, Qn and Qn will get cancelled. So what is that you're going to be left out with? Mu naught by 4 pi into Qm. Is it not looking similar to 1 by 4 pi epsilon naught into Q by r square? Right. So having this expression only, we are going to derive what is going to be the magnetic field due to a bar magnet, but at which point? At the axial point. So if you go back to some terminologies that we discussed with respect to a magnet, I told you what is magnetic axis. It is an imaginary line that is joining the poles, north and the south pole. So I need to consider a point along that line. Right. So we will take a bar magnet like this. North pole and south pole. Right. So if I take a point P here, then we will see what is going to be the magnetic field at this point. But here one point to be noted is that the bar magnet is a small one. Remember, I told you that you take the geometrical length to the magnet size to be very, very small. Right. So here I will take the magnetic length between them as 2L. The same logic is applicable. If I take this to be the center point, then this is going to be L and this is going to be L. Make sense? So from the center to the point where you're interested to calculate the field, you take the distance to be R. So from the pole, what is going to happen? This distance will be R minus L, and this distance will be R plus L. Same logic. So what is going to be the magnetic field that is generated due to the North Pole at point P. So if I say at point P, what is going to be the magnetic field generated by the North Pole? It is going to be mu naught divided by 4 pi into Q. So magnetic pole strength of both will be the same. Remember, for a given magnet, magnetic pole strength will be the same for both. So QM divided by, for North Pole, R plus L the whole square, but the magnetic field due to this North Pole at point P will be in which direction? It will be in the rightward direction. Why? Because what is the test pole that you're going to keep here? You will place a North Pole. So the North Pole, due to this North Pole, will experience a field in force in the outward direction. So it is almost similar to what you think of a positive charge. Positive charge, the magnetic field is away. Similarly, due to the North Pole, magnetic field is away. Okay. So Bn is equal to mu naught by 4 pi into Qm divided by R plus L the whole square, which is in the rightward direction. Similarly, what is going to be the value of Bs? Bs is going to be magnetic field due to the South Pole at point P is going to be mu naught by 4 pi Qm divided by R minus L the whole square. Okay, it is in the leftward direction. So what is going to be the net magnetic field? The net magnetic field is going to be Bn plus Bs in the vector form. This is what is principle of superposition. So what can you take out common? Mu naught Qm by 4 pi can be taken out common. So it will be mu naught Qm divided by 4 pi into this is 1 by R plus L the whole square minus 1 by R minus L the whole square, right? When you take the LCM and then solve it, you will have R minus L the whole square minus of R plus L the whole square, which is going to be A minus B the whole square minus A plus B the whole square. What is it? It is minus 4AB. A minus B the whole square minus A plus B the whole square is minus 4AB. Okay. So what you're going to get in the numerator is mu naught into Qm into minus 4 AB is R into L the whole divided by 4 pi into R square minus L square the whole square. So what is R square minus L square? R square. So R square minus L square is approximated to R square. So R square the whole square is going to be R power 4. So what will you get the answer as? Mu naught into Qm into minus 4 RL the whole divided by 4 pi into R power 4. So R will cancel this R power 4 3 times, right? Now, this minus I will take, see, minus sign indicates that the net magnetic field is in the leftward direction. Okay. So have that in mind. Now what I will do is, can I write this as mu naught divided by 4 pi R cube into 2 into Qm into 2L. Can I write it like this? So this 4 I broke it as 2 into 2. So one of the 2's I combined with this and the other 2 I combined it here. So what is the Qm into 2L going to be? That Qm into 2L is going to be the magnetic dipole moment. So I'll write it to the next page. So it is going to be mu naught divided by, so 2 mu naught divided by 4 pi R cube into M, but there is a minus sign here. So what does that minus sign indicate? That indicates that it is in the direction of dipole moment, because listen to this carefully. When I say minus, it is this direction. This direction is from south to north. South to north is the direction of magnetic dipole moment itself, right? Hence, what we are going to write is 2 times mu naught into M divided by 4 pi R cube times M vector, right? more than m vector. Actually, correction here, you should write it as m cap because it represents the unit vector. So it is m cap, and this is what is going to be the magnetic field which is generated along the axis of a bar magnet. Is that point clear? Done, huh? Yes. We're done with this topic. So we are almost at the end of the first part of this chapter. Okay. Can I proceed? See, when we talk about the torque on a magnetic dipole and magnetic field, right? So torque is given by the expression m vector cross b vector. So torque vector is equal to m vector cross b vector. Right. Next. If you talk about the potential energy of a dipole, this is another important thing. Okay. So when you talk about the potential energy of a dipole, right? See, let's say there is a uniform magnetic field that is existing, which is B, right? Into which you have placed a magnet, which is going to be North Pole and South. So the North Pole, due to this magnetic field, will experience a force in which direction? Will it experience to the right or left? So it'll experience to the right. Similarly, the South Pole will experience a force to the left, due to which it has a tendency to rotate. Okay. So why is it going to rotate? It will experience a torque, which was given in the previous expression. So torque that is going to experience is going to be mb sin theta. Now the question is, let's say this is rotating through a very small angle d theta, then there is a small amount of work dw that is being done on it. So what is going to be the value of dw? It is going to be tau d theta. Like how dw is equal to f into ds. In terms of torque, you can write it as tau into d theta. But what is the torque here? It is going to be mb sin theta multiplied with d theta. So mb sin theta multiplied with d theta. This is going to be the small amount of work that is being done. So what is going to be the total amount of work that is being done? It will be integral of mb sin theta into d theta, where you can say that this theta is going to vary from theta 1 to theta 2. Right? So mb will come out mb into what is going to be the integral of sin theta? It is going to be minus cos theta from theta 1 to theta 2. So take the minus sign outside. It is going to be minus mb into cos theta 2 minus cos theta 1. Right? So this is going to be the amount of work that is being done. So work done, if at all you take the cos theta 1 to be 0, if the initial angle was 90 degrees, then what you can write it as? You can write it as minus mb into cos theta when you had taken theta 1 as 90 degrees and theta 2 as theta itself. When you take it like this, you will get the value of W as minus mb cos theta, and this W is what is going to get stored in the form of electrostatic potential energy, which is given by minus mb cos theta, or you can also write it as minus m vector dot b vector. So this is what is the potential energy of a magnetic dipole in a magnetic field. It is the same logic like what we saw in the case of electrostatics. There we would have seen it as minus p vector dot e vector. Here it is minus m vector dot b vector. Okay. Right. Clear till this point? Right. So for today's class, we'll stop with this. The next class, we'll discuss about two important concepts from this. One is bar magnet as a solenoid and Gauss law. But both of them are not derivations. That Gauss law for magnet is bar magnet as an equivalent solenoid and Gauss law. Both of them do not have derivations. After that, we'll go to the next part of the chapter, which is tricky at the same time very important. So that we'll discuss in the next class. Any other questions? All clear? Then we'll wind up. Gaya, any doubts?
No, sir.
Okay, we'll wind up.
Okay, sir.